Welcome to this comprehensive lecture on inventive problem-solving techniques and methodologies. Inventive problem-solving is a systematic approach to innovation that combines creativity with analytical methods to solve complex challenges. Let's begin with TRIZ, the theory of inventive problem-solving developed by Genrich Altshuler. TRIZ was developed by analyzing patterns in over 200,000 patents, identifying systematic approaches to innovation. TRIZ works by converting specific problems into general problems, finding general solutions, then adapting them back to specific solutions. At the heart of TRIZ are 40 inventive principles that guide problem solving. For example, the principle of segmentation suggests dividing an object into independent parts. Segmentation transforms a solid block into modular parts, enabling easier maintenance, replacement, and customization. The contradiction matrix is a powerful TRIZ tool that maps conflicts to inventive principles. The matrix follows this logic. If improving parameter A worsens parameter B, apply specific inventive principle X. Consider airplane wing design. We want to improve lift, but that typically increases weight. TRIZ suggests using hollow structures or composite materials, maintaining strength while reducing weight. Next, let's explore brainstorming and lateral thinking techniques for generating creative solutions. Question: why does traditional thinking limit innovation? Because we tend to follow established patterns and mental models. Traditional thinking follows rigid pathways like a grid, while lateral thinking explores unexpected connections, like these random arrows. Alex Osborne developed 4 key rules for effective brainstorming sessions. Rule 1. Defer all judgment and criticism during the idea generation phase. Rule 2. Actively encourage wild and unusual ideas, as they often lead to breakthroughs. Rule 3. Build on and combine the ideas of others to create new variations. Rule 4. Focus on generating quantity first, as more ideas increase the likelihood of finding great solutions. Mathematically, the number of ideas generated is proportional to the probability of breakthrough innovation. Edward de Bono's 6 thinking hats provide structured lateral thinking. Each hat represents a different thinking mode: white for facts, red for emotions, black for caution, yellow for optimism, green for creativity, and blue for process. Morphological analysis systematically explores all possible combinations of solution components. This technique was developed by Fritz Zwicky and first applied to jet engine design problems. Create a matrix with parameters as rows and their options as columns. Each path through the matrix represents a unique solution. The total number of possible solutions equals the product of options for each parameter. Let's apply this to designing a new transportation system. We identify key parameters like power source, track type, and passenger capacity. With 3 power sources, 4 track types, and 3 capacity options, we have 36 possible combinations to evaluate. SCAMPER is a checklist-based technique for creative problem-solving and idea generation. SCAMPER stands for substitute, combine, adapt, modify, put to other uses, eliminate, and reverse. Substitute asks what components, materials, or processes can be replaced with alternatives. Combine explores merging multiple elements or ideas to create something new. Adapt considers borrowing solutions from other industries or domains. Let's apply SCAMPER to improving a coffee maker design. Using Combine, we might add a programmable timer. Using Adapt, we could incorporate smartphone connectivity from home automation. Biomimicry solves human challenges by emulating strategies found in nature. Question: why look to nature for solutions? Because nature has optimized designs through billions of years of evolution. Nature has had approximately 3.8 billion years to test and refine solutions. Consider a flower's radial symmetry, which maximizes surface area for pollination while minimizing material use. A famous example is Velcro, invented after observing how burdock burrs stuck to clothing. More recently, gecko feet inspired dry adhesives that can support significant weight without residue. Gecko adhesion uses millions of nanoscale structures called setae that create van der Waals forces. The adhesion force is proportional to contact area times a constant divided by distance squared. Design thinking is a human-centered approach to innovation with 5 key phases. The 5 phases are empathize, define, ideate, prototype, and test, forming an iterative cycle. Empathize means deeply understanding user needs through observation and engagement. Define involves synthesizing insights to frame the right problem statement. Ideate is the phase where we generate numerous diverse solution concepts. Prototype means building quick, low-fidelity versions to test ideas rapidly. Test involves gathering feedback and iterating based on real user experiences. Paradoxically, constraints can drive innovation by forcing creative solutions. Question: do constraints help or hinder creativity? Research shows constraints often enhance creativity by providing focus. Constraints act like boundaries that concentrate creative energy, forcing us to explore deeply within a defined space. Twitter's original 140-character limit forced users to communicate concisely and creatively. Common constraints include time limits, budget restrictions, material availability, and regulatory requirements. Innovation is a function of constraints interacting with creativity to produce novel solutions. The Apollo 13 mission exemplifies constraint-based innovation when engineers had to build a CO2 scrubber from limited materials. Engineers combined available materials in creative ways, using duct tape, cardboard, and plastic bags to save the crew. Systematic inventive thinking, or SIT, focuses on structured creativity within the problem space. SIT provides 5 thinking tools: subtraction, multiplication, division, task unification, and attribute dependency. Subtraction involves removing components traditionally considered essential, forcing new thinking. Example: removing a wheel from a shopping cart led to the 3-wheel design used in some stores for better maneuverability. Task unification assigns multiple functions to a single component, increasing efficiency. The smartphone exemplifies task unification, combining phone, camera, GPS, and computer in one device. Analogical reasoning solves problems by finding similarities with problems already solved in other domains. The principle is, if problem A relates to solution A, then similar problem B should relate to analogous solution B. Question: how do we find useful analogies? By abstracting the core structure of the problem and searching across domains. Different domains can share abstract structures, allowing solutions from one domain to transfer to another. Understanding the heart as a pump helped develop artificial hearts using pump engineering principles. The airplane wing design was inspired by analogical reasoning from bird wing structure and function. Function analysis systematically evaluates what each component does and its value contribution. Value equals function divided by cost. We can increase value by improving function or reducing cost. Function analysis identifies primary functions, supporting functions, and wasteful components that add cost without value. The process involves identifying all functions, classifying their importance, then optimizing or eliminating low-value ones. When redesigning a flashlight, we analyze each component's function and cost. This analysis led to LED technology replacing incandescent bulbs, improving function while reducing power consumption. LED efficiency is approximately 40% compared to incandescent efficiency of only 5%. Root cause analysis identifies fundamental causes of problems rather than treating symptoms. The 5 whys technique asks why repeatedly to drill down to root causes. Each why digs deeper, moving from surface symptoms to underlying root causes that can be addressed. Example: a machine stops working. Why? The circuit overloaded. Why did the circuit overload? Because insufficient lubrication caused excessive friction and heat. Why insufficient lubrication? Because the lubrication pump was not working properly. Why was the pump not working? Because the oil filter was clogged with metal debris. Why was the filter clogged? Because there was no regular maintenance schedule. This is our root cause. The solution is implementing a preventative maintenance program. addressing the root cause rather than just replacing parts. Synectics uses psychological states and analogies to make the familiar strange and the strange familiar. Synectics employs 4 types of analogies: personal, direct, symbolic, and fantasy. Personal, direct, symbolic, and fantasy analogies each provide unique perspectives for creative problem solving. Personal analogy means imagining yourself as the problem or object to gain new insights. Example: how would it feel to be a photon? This led Einstein to insights about relativity. Force connections deliberately link unrelated concepts to spark new ideas. Forcing connections between your problem and random words or images can generate unexpected innovative solutions. Evolutionary approaches use iteration, variation, and selection to evolve solutions over time. Solution fitness is a function of performance against objectives and satisfaction of constraints. Each generation produces variations, selects the fittest solutions, and breeds them to create the next generation. In conclusion, inventive problem-solving techniques offer a wide range of methods to approach challenges creatively. By applying these techniques, individuals and teams can develop innovative solutions to complex problems. Inventive problem-solving is essential for personal and professional growth, enabling us to adapt to changing circumstances and create new opportunities. Remember, innovation is a continuous process that requires practice, patience, and persistence.